Yo, yo, yo. Welcome to Today I Learned. Quick little summary. So I came across this one on Code Arena, and this one is so the purpose of this video is basically to just learn the vulnerabilities and to be able to find and protect people's capital. So the best way to learn something is to teach it. So this is my attempt, and for my future self or previous self, and anyone who may find value that's also in learning this journey. So looking forward to some feedback. So yeah, signature replay due to custom domain separator, and then I'll link these. If you could read faster than me, I'm sure you can, then I speak. So you could go through this and read them. This is my attempt at reading this and trying to understand it. So the domain separator. So to start off, this is from Next Generation. Next Generation is let's go look at their website actually. Next Generation Web3, not Star Trek. Star Trek is one, but Next Generation Web3 project. Next Generation, can you give us a link to the repo? I guess we could either repo like this. No. Copy link to submission. This is a submission. So F3S366 signature replay due to domain separator by Sandeep. Hi, 353 days ago. The domain separator is a key aspect of every signing mechanism, as it prevented the replayment of the signature. So it's a mechanism that's replaying the signature again and again and again. So it links it again and again with some specific parameters. So specific parameters are playing again and again that are unique to the contract. So to the contract, replace it again. Those parameters are usually included on the on-chain ID. Parameters are characteristics or numerical values that characterize a system. So those parameters usually include the chain ID. So a chain ID is a parameter. The address is a parameter. So there's a contract that's being verified by the signature. An example, the typical EIP 712 domain separator can be found in OpenZeppelin. So here, given already, EIPS, Ethereum, hash functions returns a hash fully encoded. This hash Solidity, digest, bytes 32, IPI encode, mail address to string contents, mail to, CAC 256 bytes, mail contents. Function, hash type data v4, bytes struct hash, internal view, virtual returns, bytes, return message hash, hash, EIP 712 domain. That's the domain, the parameters of the domain. It has the name of it, the internal views, the memory, return name string to string with fallback, name with fallback. The version of parameter, by default, this function reads version, which is immutable variable. Immutable is, it's an immutable variable, immutable is unchanged, fixed. So it's fixed. Now by default, the function underscore version is fixed. It's a fixed value. It only reads from the storage if necessary. In case the value is too large to fit the short string. So function EIP 712 version, internal view, string version, which is fixed. So return the fixed version to the string fallback version fallback. Immutable parameters, code for arena, domain control, domain separators. So this is that same one. Solid findings. I just pasted the whole thing into Cloud Code to help me understand it. Kind of looking into the open contract, backspace into it. I want to see the repo. I want to see the repo, the all threads, solutions. Can we look at the repo? Create a complete recording. Suggestions now. This is cool. All right then. Next generation. Here. Let's see if we could put in here. Sherlock, energetic liquidity character separator. This is a different one. And also, initialization process enables cross contract. Incorrect domain separator. It's a different contract. Let's go back. Stay focused on this one. So, an example of the typical EIP domain separator. EIP domain separator. Domain separator. Signature replay. Function built domain separator. Private view returns bytes. Return. CAC, let's remind ourselves of what this is. CAC character puts this cryptographic hash function. How to use creating unique identifiers and securing data. Securing data. Key aspects is utilized in Ethereum's mining algorithm. ETH, we are reconnecting. We should be live here. Going live. We're live. We're back live again. We actually just had some battery power drainage, or our battery died. And I'm gonna go ahead and share the screen. Jump back into it. Nice little break. Back into it. Back into the CAC 256 as utilized in Ethereum's mining algorithm to secure the blockchain, create unique 4-byte identifiers. 4-byte identifiers. What are 4 bytes? Byte is a unit of digital information. So a byte, digital information. Think of it like crunching with your teeth, like a bite. Digital. Like a piece of software, like you're biting a piece of software. Information, digital information. So like imagine you're biting your phone and you could bite and chew your phone. It's a unit. Like let's say you have your phone. My phone's outside, so I don't get distracted. But let's say this is a phone, but a family fully alive, building the domestic church. Solid book. But this is a byte, this is a phone. There's a piece of information on here, and it's online. You buy it. Just an analogy, right? So, historically, it was used to encode a single character of text on a computer to disambiguate arbitrarily specified bytes. An 8-bit internal protocol. The size of the byte has historically been hardware dependent, no definitive standards. Sizes from 1 to 48 bits. The 6-bit character code, character encoding is a convention using numeric character encoding, punch taped. Wikipedia encoded in American Standard Code for information interchange. information interchange. So everything's basically for sharing in information through the digital world. So going back to this, return that piece of information that is uniquely KEK Active 56 API encode, API encode, API encode deep dive into API types padding. And let's see, is this a reasonable source? API encode, which effective second pass function takes an arbitrary amount of arguments. It has bytes in memory. So bytes in memory, so it's going to take a type hash, a hash name, the hash version, the blockchain ID, the address, and this, which is this one, to return that. However, the forwarder contract, so back to the vulnerability, it replays it multiple times. Contract allows the provider to provide a custom domain separator to the signature. Signature function execute the forward request call data request bytes 32 domain separator on one line. So this one here, the forwarder contract allows users to provide a custom domain separator to the signature. Bytes request type, bytes call data, suffix data, the sig, external payable returns Boolean success, bytes memory test. So it runs through this. This will allow an attacker to get signatures that were used in the past. This will allow attackers to get signatures that were used in the past, replay them to steal the funds. So for the victim that made the signature, imagine the following example. Bob makes a signature so that the relayer can execute transfer 100 euro F from Bob to Alice on mainnet. Bob's used nonce is 0, and it gets incremented to 1. Alice gets greedy. She gets Bob's signature and call execute on the Polygon instance. The docs confirm that the protocol will be deployed on the mainnet and Polygon. Key. Because the forwarder contract allows any domain separator to be sent without checking it, Alice's transaction on Polygon will go through and steal 100 euro F from Bob. On Polygon, Bob's nonce is still 0. So the signature will be taken as valid. Because, the attack path above is prevented by the use of nonce because his nonce data is not shared between chains. It only affects the individual contract on a specific chain. This is a potential attack path, but there are multiple ways to exploit the issue. Some of the following: replay the signature after a hard fork, replay the signature. So let's see what a hard fork is. Replaying a signature, hard fork Web3, crypto, hard fork versus soft fork. A hard fork in Web3 is a radical, non-backward compatible upgrade to a blockchain that splits in 2 distinct chains. So hard fork is non-backward compatible. So think of it like a fork that always goes forward. Once you basically want a fork, you just eat the fork. And, you eat the food with the fork forward and never backward. You never go from your mouth to the plate with something, but you go with the fork to eat, never backwards, to upgrade the blockchain. And 2 different chains. It forces nodes to upgrade to the new rules, often resulting in a new cryptocurrency. So something new is created after a hard fork. So back to this, a hard fork, we play a signature that was used on another protocol. We play a signature on another chain. Recommended mitigation steps. To mitigate the issue, is recommended to not allow users to provide a custom domain separator as an argument. Instead, is recommended to always use one provided by the forwarder contract, similar to what OpenZeppelin does. Links to affected code. That's the affected code. We'll look at this shortly. Submission file touching same file. Okay. Comments on duplicate submissions. View all comments for this audit. Your CLLs, no spender can enforce. But we're sticking to the custom domain separator. Okay, we'll close this out. 2025 domain separator. Forwarder, execute, and just replace again and again. Only forward, so that could be exploited there. Web3 code for domain separator. S365 that's a comparative field. Let's break down what the finding is. The forward executor. Let's open that code again. It's this one here, hard work, domain, close this. This one, function execute. Forward execute function accepts a domain separator as a called supplied argument rather than computing it internally. EIP 712's domain separator exists precisely to scope a signature to a specific contract plus a chain. If you let the caller provide it, you've nullified that protection entirely. The canonical fix is what opens up and does. Function, build a domain separator. Private view, return the bytes, return KCAC API encode. Hashed version, blockchain ID, address this, blockchain and address are two anchors. Remove either one from the attacker's control. And cross-chain, cross-contract replay collapses. Why it's high and why the judge agreed. The judge's rationale is worth studying. Yeah, for sure. The in-scope documentation states the system is expected to be deployed across the distinct blockchains, rendering the attack feasible. This is a key detail. Without multi-chain deployment confirmed in scope, this might have landed as a medium. The attack requires the same contract address across chains, or at least the same trusted forwarder, which is not trivial. When the docs confirm multi-chain deployment, the attack path is direct and severity is locked in as high. Lesson: always cross-reference the protocol docs for deployment context. If vulnerability severity often lives or dies on facts outside the contract code. With the primary submission, S3 probably better. Your submission was good. It's not my submission. The primary likely differentiates itself as catching this deadline, take away context. If a Solidity contract lets you pass your own domain separator, signatures replayable across chains. Domain separator, perfect returns, chain binding, contract binding, chain binding, contract binding. The forwarder contract. The forwarder contract decided to do something different. It lets a caller supply the domain separator. Supply what the? It let callers supply the domain separator as an argument to execute. Caller control. Function execute. Function is to execute for request call data, the domain separator. Caller control, domain separator, bytes, 32 request type, bytes, call data, suffix data, bytes, call data, sig. That's the bug. The moment you accept domain separator from the caller, you've handed them control over the scope of every signature the protocol processes. The attack is straightforward. Block signs matter transaction, hits not synchronous to one. Alice grabs a signature, calls execute. Yeah, Alice calls executes this one on Polygon, passing in a domain separator. This one, Alice grabs a signature in Polygon, passing a domain separator that makes the mainnet signature look valid on the mainnet. Pops nonce on Polygon is still 0. Check passes, funds move. Nonces don't save here. They're chain local. The same nonce can exist independently on every chain. The protocol deploys. What makes high severity is deployment context. The context of the deployment. The protocol docs confirm systems that will want 3 chains. So there's 3 chains that they confirmed. So there's 3 different chains. Without that, the attack requires the attacker to also control the target address. Across chains is harder. Without the 3 different chains, on the blockchain. Without that, the attacker requires the attacker to also control the target address. Target. With it, the path is direct. The fix is a single architectural decision. Don't accept domain separators from callers. Don't accept domain separators from callers. So if they could call this function call data domain separators from callers, don't do that one. This was one of the 36 valid duplicate findings in the code for Arena audit. Code Arena, not for Arena. Code for Arena. Code Arena audit, which tells you two things. The bug class is well known enough to be caught at volume, and the protocol still shipping it means it's also easy to miss and review when you're not running a systematic signature checklist. Signature checklist is key. Systematic signature checklist. To the node signature checklist. Yes, we're already doing signature checklists. We gotta make sure the signatures are in order, just like when you send out a document for an approval and designs, it has to do. It's more efficient that way. It's efficient to have systematic review of signatures. So Bob signs a message, the relayer calls. Okay, transfer, copy the clipboard down to Alice. Bob signs the message. Bob signs the message, so they accept the relayer calls, execute, forward, verify, signature transfer. Step 1, Bob sends a meta transaction. Bob wants to send to Alice via a relayer meta transaction. What he signs from Bob, send value 100 notes. Nothing's happened yet. It's baked into how the forward process the signature. Forwarder. Here's a forwarder. Request a call data. Attacker controls this. The domain separator. Guess what's being attacked? The EIP 712 spec says the domain separator should encode chain ID and address this, making signature chain and contract specific, accepting that as an argument that was guaranteed away entirely. So record the interactive widgets itself. Well, the interactive widget. Is this interactive? Okay. Legitimate relayer executes on mainnet. Execute required domain mainnet. Nuts 0. Transfer execute. Nuts mainnet. Nuts polygon still 0. Nuts chains are local. There's no shared data. Polygon execute domain mainnet. Bob sig matches. Transfer executes again. Because there's one on the mainnet, gets a +1. The sig matches. The signature matches from this one. The signature that Bob accepts, I believe. And then Bob's signature is still valid on Polygon. That's a 0 and used there. Why it works. Alice's passes the same domain separator. The relayer used on mainnet. The forwarder doesn't check if it matches the current chain. Bob's nuts on Polygon was 0. The sig valid funds leave Bob's wallet on Polygon. Function build domain opens up a pattern computer never accepted from caller. Function build domain private blockchain ID return go type hash name blockchain ID caller supplies domain set any chain any contract can verify replay. Contract computes domain separator. Contract computes the contract computes the domain. Scope to on-chain. Scope to on-chain plus address. Scope to on-chain. Scope to on-chain plus address. Oh, it's scope to it. So the domain separator is sent to chain binding. It binds it on the chain. This is like send it to the chain. The address, the domain separator. Checklist. When auditing signing mechanisms, is the domain separator caller supplied? Does it include chain ID? Does it include address? Does it include address this? Is there a deadline? Are nuts cross-chain or local? Okay. So again, that contract domain separator function execute. Let's see who is executing the domain separator. The attacker controls this. Whoever is that one. Code walkthrough, Forger, file, yes, code use Loom. Scripted, script. My honest take, Loom interactive widget. Well, kind of did that. I was like, I want to read this contract, the domain separator. Cool. I'm going to look at some contracts, but that was a vulnerability that we're learning. So thanks. See you in the next one.